Hey everybody, this week we're going to be talking a little bit more about electron treatment planning, okay? And to do that, we're going to use this case right here. This was a AAMD plan challenge case from 2017. We're going to focus on just a couple of the targets. This was a pretty difficult case. If you haven't done it yet, go check it out on Prono. Again, the 2017 AAMD plan challenge. You can run through it yourself. It's a good case to get some experience with. But anyways, as we can see here, we have this very large GTV of the left ear. Okay, it's a very severe skin cancer case. And when you see something like this, one of your first thoughts should be, can we treat this with electrons? And we're gonna try to do that right now. All right. Before we get started though, let's take a look at just a couple of things related to electron planning. So there's a few things to kind of be aware of, right? The first is this picture right here. So this will show up in a lot of textbooks and probably on your boards and everything. There's a few basic metrics. When you're actually planning, this table right here can be helpful to kind of have at least you don't have to memorize it per se, but for example, to get started, to choose my energy when I first get started, I kind of measure the depth that I want to treat to. And if you multiply that depth by 3, you can get a good approximation of what energy you should at least maybe start with. So for example, if I measure the depth of my target and it's 4 cm deep, I just take 4 times 3, 12 MeV. And that comes from this right here. So the R90 value of 12 MeV beam is about 4 cm. So if you take all these, so if we do 5 times 3, 15 MeV, right? 3 times 3, 9 MeV. So you can kind of measure your depth and get a good starting point on an energy, all right? The next thing to keep in mind is electrons are opposite of photons. As you increase in photon energy, your surface dose goes down, right? Well, as you increase your electron energy, the surface dose goes up. So you can see here the surface dose of my 6 MeV beam right here in blue. Down here, as you get up to 20, the surface dose goes up. As you increase electron energy, your treatment depth goes up. And also you should keep in mind that your Bremsstrahlung increases with energy too. So the photon leakage you'll get out the back of your treatment area will go up as your energy increases. The next thing to kind of keep in mind is that low energy electrons, the penumbra region on the side here has a little bit less constriction, meaning that the distance from your 100% line to your 50 or to the block edge will be less than with higher energy electron beams. High energy beams tend to kind of constrict in the middle, have a very wide penumbra region on the edge. And so this is important when you're drawing your block edge. You need to understand that if you're going to use a high energy beam, you're going to have some dose kind of spill out maybe past your block edge. So if you're trying to block like a lens, for example, know that with a high energy beam, you're going to have a little bit more issue with dose getting to that lens, even if you're blocking it. And the other problem is with a higher energy beam, you will likely need a larger margin on your block in order to get good coverage because of this issue. All right. Field size, you can see the your max dose goes up with field size. Your dose at depth goes up with field size, and that's because you have an increased amount of scatter coming off your block, okay? And I think that was it for this one. The last thing I want to kind of show you guys is this picture right here. You should always keep this in mind too. So if you look at the surface that you're treating, if you have a big indent like this big indentation, you're going to end up with hot spots on the insides of those indentations. If you have a big projection right here like this, you have hot spots on the outside of those projections. So again, just a good way before you even calculate dose, as you're setting up your beam, drawing your block, coming up with your gantry angles, your catch angles, all that, going to keep all these things in mind in order to kind of predict what you're going to get once you calculate. And so having said all that, I mean, all that stuff is good information to know. You need to know it. You need it for boards especially. These days though, we rely on our treatment planning system. So you're going to set something up, calculate it, evaluate the actual dose distribution, and make decisions based on that. That's how most places do it. We'll still do hand calcs and simple stuff like that for simple electron cases, but for complicated ones like this, high doses, anything that's not flat, nowadays usually we do a CT based plan so we can evaluate the dose distribution. But having said that, it's still important to kind of keep those things in mind, because a lot of older physicians will still kind of keep the old hand calc ways in mind as they're planning and setting things up. And the other issue is we're moving to Monte Carlo based planning for electrons especially, and the calculation time goes up significantly. So it used to be pencil based, all these treatment planning systems, and the calculation was pretty quick but not very accurate for electrons. Now we're moving towards Monte Carlo algorithms to calculate these electron plans. A lot more accurate, but it takes a lot more time, and so we'll demonstrate that right now. So let's go ahead and set up an electron case for this right here. So the first thing we need is a bolus. I'll show you two ways to set up a bolus in version 16. One of them is new for version 16. So let's insert new bolus. Call this bolus for the ear. All right. So the default way in version 16 is this edit bolus on body tool. So it's kind of neat. Usually it works really well. So what you do is you can put your thickness in. You can use these drawing tools to actually draw on the body exactly where you want and the exact shape that you want this bolus to be. Just like that. So usually it works really well. Usually I really like this tool. This is a good example though of when this tool might not be the best. So you can see what it does is it actually it lays a bolus on as a projection onto the body. This target though, and the surface of the body is kind of a little crazy, right? We have these real steep areas on the sides, and so it actually breaks the bolus up in spots. So you can see over here, if we rotate over here, you can see where the body kind of indents in right there. And over here, it's actually broken up. So maybe a situation where this tool is not the best. So we can go ahead and clear that out, close this. The other way to do it is if you right click on your bolus, you can edit bolus with VOI. This is this way of adding a bolus in Eclipse has been around for a long time. So what you do is you edit your VOI box to cover everywhere you want that bolus to show up against the body. So maybe something like that. Again, we'll put our thickness in, say OK. And it's going to just add a bolus right up against the body contour everywhere inside that VOI box. All right, so again, if you want to edit that, you can just right click, edit bolus with VOI box again. You can edit your box if you want to, and redo that. So the only downside to this tool is that, you know, it's going to be a square shaped bolus. So if you want that custom shape of a bolus, it's much easier to use the edit bolus on body tool. All right. So the benefit of this tool is we don't have that problem. The bolus doesn't break up, but we can see here it's going to lay that bolus on the body exactly how the body is. If we look here, you know, the bolus is going kind of in and under this this GTV, and you know, it's in all the nooks and of the body and everything. Obviously, in real life, in the clinic, we're not going to be able to get a bolus that conforms this well to the body. So you always got to keep that in mind too. So what you can do is, you know, kind of flatten out the body. So as an example, we already have calculated plans on this body, so I won't actually show you, but what you can do is you have to kind of be realistic, right? And imagine what the therapist can actually do in the clinic. And so I know I'm not going to get a bolus that kind of goes into this little divot right here. So you could smooth out the body and simulate where you think that bolus could realistically lay, right? So they're just gonna, if you're just using like a super flat bolus, you know, piece of bolus, it's gonna just kind of lay over top of here, so you can kind of smooth out the body and get that bolus to kind of portray what's actually going to be happening in the clinic. All right. For this example, we'll just leave it as is. But if I was really going to do this with a bolus in the clinic, I would be kind of smoothing this body out so that I could get a bolus to lay a little bit more realistically on top of this target. All right. Okay, so we got our bolus. Let's insert a new plan. All right. For the time being, let's just pick 12. It's a pretty big target. Let's do 15. So to slow down a little bit, I just picked 12E for now. All right, it makes you choose an energy. As soon as you choose an electron energy, so all these E's mean electrons. So this is a 12 MeV beam. As soon as you do that, the accessories tab turns orange because you need to add an accessory mount here. So we're going to use a 15 by 15 cone. All right, so you have 6 by 6, 10 by 10, 15, 20, 25. All right, so I just chose 15 right now. It's going to ask you, since you chose electron as your energy, do you want to change the technique to fixed SSD? Yes. Generally, when you're treating with electrons, you're going to do an SSD-based plan, meaning you're going to set up so that your beam is just 100 cm SSD to the skin. Or if you need to do it a little bit extended, you know, 101, 102, but that's how the therapist will set this up, is they'll make sure that your SSD is 100. All right, so we can set that right here. Oh, whoops, facing the wrong way. There we go. So different clinics will do electrons differently. A lot of clinics will maybe put a BB right where they want the ISO to be, or something like that, or a lot just will place it in the center of the target. So what's important with electrons, so first off, our 15 by 15 cone right here is going to be a little small. So let's right click on our field, go to properties, go back to accessories, change that to 20, 20 looks like it'll be big enough. So now we have a 20 by 20 cone. Our SSD was 100. Our ISO is about in the center of the target. Next, we need to come up with our gantry angle. So with electrons, we want to be as en face as possible. And what that means is we want to be as perpendicular to the surface of the body as possible. Obviously, we're not dealing with a flat surface right now, so you just have to kind of come up with an average, right? You want to be perpendicular to kind of the average of the surface. So maybe a little more that way, maybe something like this. All right, and then if you can, you should also look at whether or not a couch kick will help you. So, I really don't think so. The couch at 0, we're pretty perpendicular in this plane as well, so I think we can just leave it like this. All right. Next, we'll add a block. So right-click on our field, new block, material code, electron block, type aperture, tray. Again, depending on how your clinic operates, you might do things a little differently, but we'll just select custom FFDA. And what that does is if you're using a TrueBeam or a variant machine, you can, each tray has a custom, or each block has custom code associated with it, and the machine can see that code. So if the tray has the code 3366 on it, if they put the wrong block in the machine for treatment, it'll alert them that the wrong block's in there. It won't let them treat unless they have the right tray in the machine. So it's just a little bit of a safety measure. All right, we got our block. I'm going to right click, fit to structure. I'm going to fit to my GTV. Again, it's going to depend on what your doctor wants. A lot of times when you're dealing with a GTV, you would do a 2 cm margin. This is a ginormous target. It's protruding out of his body. It's very easy to see. It's going to be very easy to set up. So for all those reasons, maybe we'll just do 1. Something like that. All right. A lot of times I like to kind of smooth it out. So where you see these kind of sharp points or something like that, I'll kind of just get rid of them. Whoops. Maybe. It is not liking that. I have to add. There we go. A lot of times when they cut the block, all these will kind of smooth out anyways. So I don't know, I just look for those kind of pointy spots of the block and I smooth them out a little bit. Okay, looks good. Right click on my field. I'm going to link it to my bolus, the bolus ear that I made. All right. Prescription, I don't know, we're going to make something up. Let's do 200 times 30. And calculate. All right, so with Monte Carlo, like I said, the calculation is quite a bit more accurate. It's a lot more robust calculation. Takes a lot longer time. So again, all those graphs and things I showed you, it's a good idea to have a basic understanding of all of that and your electron energy and everything. to be able to kind of guesstimate what you're going to get before you calculate, because it takes so long to calculate. Every little change you make, I mean, you have to recalculate, right? So it just, if you can kind of predict what you're going to get ahead of time, it'll just help you out in the end. All right, and something we forgot to do is take a closer look at our energy. So if I measure the depth, my depth is 5, almost 6. So we're gonna need something maybe closer to like 18 MeV. Right here we get really deep. Closer to 7. So what I'm gonna do, 6 to 7, so 18 to 21, right? So let's try 20. It's just warning us that the jaw settings are going to change because we made that change to 20E. It's fine. Calculate. All right, guys, finally done. So as you guys saw, it took almost 20 minutes, okay? And it's one of the big bummers of Monte Carlo. But the reason why we use it is, again, because it's quite a bit more accurate for electrons especially. The reason why it takes so long is because what EMC is actually doing is it's tracking each individual electron through the patient and then calculating the energy deposited into each voxel along that electron's path. So if you think about it, a lot of electrons, right? So it just takes a while for it to do all that computation, all right? The bigger the fields, this is a pretty big electron field, so it took quite a while. Okay, so again, every time you want to check on a little edit, if you want to edit your Gantt angle just a little bit or change energies or anything like that, you got to go through that every single time. All right, let's look at our plan. So for electrons, most of the time, most people start by normalizing to the 90% isotose line. All right, so we just normalize 90% isotose line. That means this blue line is now our 100% line. So blue line equals 6,000. A lot of times that confuses people, so a lot of times we will change to absolute, rescale, so that our usual 100% color, red, is now our 100% line again. Okay, so a few things to note. Our energy selection, not terrible, right? In general, we're treating to the correct depth. It looks like we had a 22. We used 20E. We could have used 22E, maybe, and got a little bit better plan. Got a little bit deeper. Hotspot is very hot. 96 gray, and it's right where we would expect it to be. All right, if we, I think I closed those pictures, but you see we have this big projection, right, and this big drop off, and it's putting a huge hot spot right on the outside of that. All right, so before even calculating, we knew it was going to do that. That's what electrons do, all right? The problem with this case is how do you get around that? The tumor is just projecting that far, right? You can build up the bolus more on the edges of the tumor to prevent these big hot spots, all right? But in general, you know, for this case, if we look at our coverage, it's not great. So 6,000 is only covering about 84%. This huge hot spot. We're using such a high energy that, I mean, if you look at our line, so 3,000 is, you know, it's not penetrating super far. But what I'm about to discuss is, you know, this is probably a good, you know, even though this is skin cancer, and even though maybe since it is superficial disease, your first gut instinct is to try electrons, and you should try electrons for stuff like this, but this is probably a better case for photons, right? There's no reason why we can't use simple APPA photon technique and get a much better dose distribution. We're not going to be treating any more normal tissue than this electron plan, and arguably, you know, maybe we can get by with treating less, right? Again, because we're having to use such a high energy, we are having dose penetrate pretty deep. Okay, so before we move on to photons for this case, I just wanted to also just kind of explain a little bit what Eclipse is doing and how it's calculating its monitor units, because right now we're set to no planned normalization, and we're just normalized to 90% isotopes sign. We're not normalized to a point or anything like that. What Eclipse does automatically is it's going to put 100%, so 6,000 at Dmax right underneath the isocenter. So if we go to our isocenter, if we switch back to 100%, at Dmax, so whatever we have Dmax set at in Eclipse for 20E, which I don't know the exact number, but it's probably somewhere around 4.2 is what we have it set at. It'll normalize our monitor units, our plan, so that it's putting 100%, so in this case 6,000, right at Dmax under our plan. The equivalent Dmax depth, so not the physical length, it'll look at the equivalent depth. So it'll take into account, you know, densities, right? So if there's bone in the way, air in the way, it'll be the equivalent depth right underneath the isocenter. And the problem is that because of what I just said, right? It's looking at the equivalent depth. So a lot of times what you'll end up doing is you'll compare this calculation to, you know, hand calc or rad calc or MU check or some sort of second MU check software, right? Those softwares are assuming a flat surface that you're treating, a homogeneous surface, so just water. It's just comparing a hand calc on a water tank, basically, right? And this is far from that perfect scenario, right? In this case, it's probably going to be pretty close because this tumor is very large and it is fairly homogeneous and, you know, fairly flat, at least in the area of the isocenter. So in this particular case, probably not a huge problem, but when you get like a nose or a cheek or something, all this bone and air in the way, it's going to significantly shift that effective depth underneath the isocenter. It's going to significantly shift that Dmax, you know, location and the location that Eclipse is normalizing to. And it can have a big effect on the monitor units that Eclipse is calculating. All right, so what do you do when Eclipse is disagreeing with those second check software MU? That's kind of something that clinics struggle with, how to properly deal with that issue. But I just want to make you guys aware, that's what Eclipse is trying to do. It's looking at that Dmax depth underneath the isocenter, normalizing 100% to that. If Dmax is more than if the max dose underneath the isocenter is more than 50% different than the global Dmax. So in this case, the global Dmax is 8650. If we do 8650 divided by 6,000, that is 144%. So it's still only 44% off. So it's still, in this plan, normalizing underneath the isocenter. If the global Dmax is more than 50% different from the Dmax under ISO, it'll actually normalize to the global Dmax. All right, so if you get something really weird looking and with a really large hotspot, it might look that weird because it's normalizing now to the global Dmax. So long story short, it's important to really understand how Eclipse works, how your treatment planning system works, to help you kind of problem solve and figure out solutions to some of these problems. Long story short, though, probably my suggestion would be not to use electrons for this case. We could very, very easily do a photon plan. So it is a GTV, so let's do at least that 1 cm. But in this case, I would open up these outside MLCs, give ourselves some flash. You could try to, rotate your gantry angles to get as tangential as possible and match this medial border here with your MLCs. Probably not super important for a case like this. I want to definitely make sure we're not exiting, hopefully, through the eyes or entering through the eyes. Nope. Still going to use my bolus. I would maybe use a new bolus. Let's see what it looks like. Yeah, maybe I would want to redo my bolus to make it easy on the therapist and just cover the whole field. If you don't want to cover the whole field, though, you don't have to, and I'll show you in a second a little trick on how to tell the therapist what shape your bolus needs to be and where it needs to lay. Let's see, our separation is only 15, so 6x, probably fine. This is a GTV, so I want pretty good coverage. So yeah, there you go. I mean, you can see, so let's use the eye as a reference. I mean, our 50% line, right, is going to be right up against our block edge. We're going to have very little lateral scatter from this photon plan compared to, this high energy electron plan. Again, using the eye as a reference, you can see we're getting pretty good dose to the eye, and the 50% is, all the way to the eye. So again, just because it's a skin cancer or surface, related, does not necessarily mean electrons are the best option. Okay, so this plan, we could play with normalization a bit. Otherwise, we would use our field and fields or EDWs to plan this, cool it off, and be done. All right, last but not least, one quick, easy way. Pretend we wanted to use this bolus. The bolus does not cover the entire field on both sides, right? And so because of that, we need to tell the therapist where to put the edge of the bolus, right? They can't just cover the whole field in the clinic when we didn't plan it that way. That'll affect the dose distribution, right? So an easy way to kind of handle that is you can insert a setup field that they will be able to load up on the machine. We can temporarily attach our bolus to that setup field. And then you can use your JAWS or MLCs, whichever. But you can just outline the bolus. Something like this. All right, so we outlined the edge of that bolus. You can't have a setup field with a bolus attached, so you have to attach it, draw your field, and you remove the bolus when you're done. But now if we look at our body, what they'll be able to do is load this field up. There we go. There we go. Okay, they'll be able to load this field up at the treatment machine and look at the light projection of the field, right? And that light projection will show them the exact border of the bolus on the patient. So then, they can lay a large piece of bolus on this guy's treatment area, draw that light field, then cut it out, and lay some marks on his skin maybe to help them place that bolus every day. All right, so we use that trick quite often because in our clinic we do a lot of custom. We go through a lot of bolus, do a lot of custom pieces of bolus. But if your clinic doesn't want to cut up a lot of bolus, you can just make it bigger too and cover up your whole field. All right, that's it for this week. If you have any questions on any of that material, please reach out and let me know. Thank you.